Good morning, all of you. Our next session that is regarding the newer methods of synthesis. So far we had seen some of the basic principles of green chemistry and regarding the atom economy also, and how we can replace some of the chemicals or the solvents used, okay, in organic synthesis. See here, in this newer methods of synthesis, we are using some alternate method for carrying out a reaction. Okay, we are using a newer method or some other methods. That means instead of supplying heat or instead of supplying heat energy, we are using some microwave radiations, or we are using some other. For example, we are using this microwave radiation or ultrasound radiations, etc., for the organic synthesis instead of having a heat supply. Okay, so then the first one we have to discuss in this newer methods of synthesis, that is the microwave assisted organic synthesis. Okay, you have seen this microwave oven, isn't it? So in that microwave oven, which radiation is used? Microwave radiation, it is used there. Microwaves are used there, and also this microwaves, it has got a the property of this microwaves is that they have got a permanent dipole. For a molecule to be microwave active, it should have a permanent dipole moment. So only that molecules will be microwave active. Okay, so the molecules with permanent dipole moment, it will be microwave active, or it will be excited by while during the supply of a microwave radiation. Okay, so here instead of having heat energy, we are supplying microwave radiation. Usually this microwave radiation, it will be we are cooking food using this microwave oven. It will be taking a very few minutes instead of hours, isn't it? We can cook anything with some minutes itself. So that is one peculiarity of this microwave oven. And also the time, we can save time, and also we can save energy as well. Normally, if we are cooking food in our normal gas system, what happens is that some of the energy is consumed by this vessel itself, isn't it? But in the case of a microwave oven, what happens is that the energy will be completely absorbed by the reacting substances itself, not by the walls of the container, or not by the vessels of that particular reacting substance, or the food which is being cooked. Okay, or the vessel by which the food is being cooked. Okay, so we can save time as well as energy by using this microwave oven, or we can use by using this microwave radiation. Okay, so that is one of the important point regarding this microwave assisted organic synthesis. There we can save a lot of time as well as a lot of energy. And so we can say that this microwaves, it is an alternate source of energy, and their molecules will be active if that particular molecule will be having a permanent dipole moment. And also this microwave induced organic reactions, it can be carried out. This microwave induced organic reactions, it can be carried out either in the presence of a suitable solvent. See, normally organic reactions, they are carried out in presence of some solvent, isn't it? And sometimes it can be carried out using solvents, or without solvent. That means with the help of a solid support itself, or without solvent, we can carry out this organic reactions using microwaves. And also, while we are using solvent for a reaction to take place using microwaves, some characteristics should be there for this particular solvent. Okay, the solvent should have some important characteristics for for carrying out the reaction in presence of this microwaves. Okay, so the first characteristic property is that the solvent should have a permanent dipole moment. The solvent should have a dipole moment, should have a permanent dipole moment, or it should be somewhat polar in nature. If only the solvent is having a dipole moment, what happens is that it can absorb a microwave radiation. Otherwise, this solvent cannot absorb a microwave radiation. So, the first important characteristic for a solvent to be microwave active is that it should have a permanent dipole moment. And also, again, one more point is there. The second point is that The boiling point of the solvent, it should be about 20 to 30 degrees Celsius higher than that of the reaction temperature. The boiling point of the solvent, it should be 20 to 30 degrees Celsius higher than the reaction temperature. Suppose if the reaction will be carried out at a temperature of 160 degrees Celsius, then this boiling point of the solvent, it should be above 190 or 180 itself. Okay, so that is the another characteristic feature of a solvent to be used in while we are using this microwave radiation. Okay, so these are the 2 points to be noted. First one, it should have a dipole moment, and the second one, it should have a boiling point greater than 20 to 30 degrees Celsius should be greater than the particular reaction temperature. The boiling point of the solvent should be greater than this reaction temperature, nearly about 20 to 30 degrees Celsius. Okay. And also in your textbook, there is one example is given, that is DMF. DMF is a solvent which is used for this microwave assisted organic synthesis, and this DMF, it is NN-dimethyl formamide. DMF is NN-dimethyl formamide. NN-dimethyl formamide. Okay, so this NN-dimethyl formamide, it has got a boiling point of about 160 degrees Celsius. Boiling point of dimethyl formamide, it is 160 degrees Celsius, and also it has got a dielectric constant. See, normally dielectric constant, it will be denoted by epsilon. This dielectric constant, it is equal to 36.7. That means it is somewhat a higher value. That means the dipole moment is very high. Okay, so the dielectric constant, it is 36.7, and also the boiling point is 160 degrees Celsius. So we can say that it is a very good solvent for microwave assisted organic synthesis. Okay, so DMF, it is a good solvent. That means it will be it will satisfy the 2 conditions. Okay, for a good solvent. Then normally while we are doing an organic reaction at a temperature, that is without microwave, that means we are using solvents such as hexane, then benzene, toluene, etc. Hexane, benzene and toluene we are using as the organic solvents normally in our lab, and this hexane, it has got a dielectric constant of about 1.9. Then benzene, it has got a dielectric constant of 2.3, and for toluene, it is about 2.4. That means they are not good solvents. That means they are not good solvents. So we can say that this DMF, sorry for all the noises going on here. Okay, so DMF, it is a very good solvent, but at the same time this hexane, benzene and toluene, since the dielectric constants are very low, see, in the case of DMF it is about 36.7, but in the case of hexane, benzene and toluene, it is about 1.9, 2.3 and 2.4. So we can say that they are not at all good solvents. Okay. So it has got a lower dipole moment, as well as since it has got a lower dipole moment, it will not absorb this microwave radiation so easily. So that we can't use this as use this as solvents for microwave assisted organic synthesis. Okay. Hope you are clear up to this regarding the microwave assisted organic synthesis. Then the next is the advantages of using this microwave assisted organic synthesis. Okay, advantages of using microwave assisted organic synthesis. And here this the first advantage is that this microwave assisted heating or the microwave radiation, it is more efficient than conventional heating. Microwave assisted heating, it is more efficient than conventional heating. More efficient than conventional heating. It is more efficient than conventional heating. Then the second one, the second advantage is that the energy that we are supplying to the reacting substances, it will be directly absorbed by the reacting substances. Okay. The energy that we are supplying, it will be directly absorbed by the reacting substances. it will be directly absorbed by the reacting substances. Directly absorbed by the reacting substances. That means while we are using conventional method of heating, what happens, some of the energy will be absorbed by the reacting vessel itself, isn't it? But here in the case of microwave assisted synthesis, the energy will be directly absorbed by the reacting substances itself. So it leads to this less consumption of energy, isn't it? And also this microwave assisted synthesis means it will be having, normally it will be having a rapid heating. That is, the time taken will be very low, and that means it will be having rapid heating, and also it will be saving our time also. Okay, it will be saving time. Then the next one, that is this microwave assisted synthesis, it is eco-friendly. It is eco-friendly. Either we can use solvents. Sometimes we can eliminate the use of solvents, isn't it? In some reactions we can eliminate the use of solvents by using microwave assisted synthesis. In some cases we can eliminate the use of solvents, or else we can reduce the use of solvents. Anyway, it is a greener method of organic synthesis, isn't it? Either we can eliminate or we can reduce the amount of solvents to be used in a particular organic reaction or in a particular organic synthesis. So these are some of the advantages of using microwave assisted organic synthesis, and also it is pollution free while we are using this microwave oven, isn't it? So these are some of the advantages of using microwave assisted organic synthesis. Then again, one more topic, that is microwave assisted organic synthesis. It can be classified. This particular synthesis, microwave assisted organic synthesis, it can be classified into 3 categories. Okay, microwave assisted organic synthesis can be classified into 3 categories. The first one, that is the microwave assisted reactions in water. That is the first category, microwave assisted reactions in water. Then the second category, that is the microwave assisted reactions in organic solvents. Microwave assisted reactions in organic solvents. Then the third one, that is the microwave assisted reactions in solid state. Microwave assisted reactions in solid state. So these are the 3 main classification of this microwave assisted organic synthesis. First one, the reaction will be taking place in water. Second one in organic solvents, and the third one in solid state. Then you have to go through one by one. Some of the examples also you have to go through. The first one we can go through, that is the microwave assisted reactions in water. Okay, so write down the heading, microwave assisted reactions. Microwave assisted reactions in water. Microwave assisted reactions in water. Okay. So first example given in your textbook, that is the hydrolysis of benzyl chloride. Hydrolysis of benzyl chloride. Hydrolysis of benzyl chloride. See here, this benzyl chloride is C6H5. It is YL, benzyl. That is means benzyl means C6H5CH2Cl. Okay. If it is benzoyl, then it will be COCl. Okay. So C6H5CH2Cl, that is benzyl chloride. Benzyl chloride on hydrolysis. Hydrolysis means addition of water. So here we are using microwave assisted synthesis of this benzyl alcohol. Okay, so the product will be benzyl alcohol, C6H5CH2OH. So here the Cl is replaced by an OH group. So here it is done using a microwave assisted synthesis, and it will be taking only 2 minutes for the reaction to take place. Okay. And also the yield of this benzyl alcohol. So this is benzyl alcohol. The yield of benzyl alcohol, it is about 97%. See, it is atom economical, isn't it? The yield is 97%, and we can say that. So this particular reaction, it is a green reaction, or it is microwave assisted reaction. See, the time taken, it is just 2 minutes, okay, for the reaction to complete. But normally, if the hydrolysis is carried out in normal or conventional method, it will be taking about 35 minutes. See the difference in the reaction time. So by conventional method, it will be taking 35 minutes. But while microwave assisted synthesis, consider the time taken as well as the yield. The time consumed, it is about 2 minutes and the yield is about 97%. So these are some of the advantages of using this microwave assisted organic synthesis. You can save time as well as energy, and also the yield of the reaction will also be very high. So the next example, that is the hydrolysis of benzamide. Hydrolysis of benzamide. See here, benzamide, the formula is C6H5CONH2. This is benzamide. I think you all know the formula also. C6H5CONH2 benzamide in the presence of 20% sulfuric acid, 20% sulfuric acid, and this is also a microwave assisted synthesis. The product will be, see, the hydrolysis of any side chain product, the hydrolysis becomes, the product becomes HOH. So the product will be C6H5COOH. Here it becomes NH3. Okay. So our major product is benzoic acid, C6H5COOH. Benzoic acid hydrolysis takes place here, that is at this portion the bond will be broken and water will be splitting as H and OH. Hydrogen will be coming here, OH will be coming here. So the product here it is C6H5COOH. Here it becomes NH3. Okay. So the product is benzoic acid. Here also it is a microwave assisted organic reaction, and for the reaction to take place it will be taking only 7 minutes to complete the reaction. The yield is about 99%. See the yield, it is very high, isn't it? 99%. And also if we are doing this hydrolysis by a conventional method, it will be taking about 1 hour for completion by conventional method. Okay. So you see the difference. Here it will be taking only 7 minutes and the yield is 99%. So it is a better way, isn't it? By using microwave assisted synthesis, it is a better way to carry out the particular synthesis. Okay, next the third one, that is the hydrolysis of N-phenyl benzamide. Third one, hydrolysis of N-phenyl benzamide. Hydrolysis of N-phenyl benzamide. See here, N-phenyl benzamide, the formula it is like this. N-phenyl means the bonding, it is through the nitrogen atom, isn't it? So this is a benzene ring. N-phenyl benzamide. Benzamide is C6H5CONH2, isn't it? So CONH2, instead of two hydrogens in NH2, one of the hydrogen it is replaced by another phenyl group. Okay, NHC6H5. Okay, so this is phenyl, this is benzamide, CONH2. So this hydrogen it is replaced by a phenyl group. Okay, one of the hydrogen replaced by a phenyl group, so it becomes N-phenyl benzamide. See here, the linkage of this phenyl group, it is through this nitrogen atom. Okay, so this is N-phenyl benzamide. N-phenyl benzamide. So this N-phenyl benzamide, on treating with 20% sulfuric acid, this is also a hydrolysis reaction, and the reaction is carried out in presence of microwave radiation, and it will be taking 12 minutes to complete the reaction. The product, see, any side chain reaction, the side chain will be converted to OH. Okay, here if any number of atoms are present here, the product will be benzoic acid. At this point the bond will be broken and the product will be benzoic acid for the hydrolysis reactions in general. Okay, so the product will be again C6H5COH and the remaining product will be C6H5NH2, isn't it? Or aniline. So here benzoic acid is formed, and also the yield is about 74%, and also the time taken, it is only 12 minutes to complete the reaction, and the yield is 74%. And by normal hydrolysis, or by using the usual procedure for hydrolysis, it will be taking 18 hours to complete this reaction. Okay, using conventional method or by normal hydrolysis or by normal heating, it will be taking 18 hours. So instead of 18 hours, we can do this reaction within 12 minutes itself, and also the yield is about 74%. Then the next reaction, that is the saponification of methyl benzoate. Saponification of methyl benzoate. Saponification of methyl benzoate. Here also we are using a microwave assisted reaction. See here, methyl benzoate, that is C6H5 COOCH3, ester group COO, isn't it? So this is methyl benzoate. Methyl benzoate, I think in the textbook the name is written wrong. You have to correct it. This is methyl benzoate. And here saponification, it takes place in the presence of sodium hydroxide. Normally saponification is done in the presence of an alkali, isn't it? So a strong alkali, that is sodium hydroxide, is used, and we are using microwave assisted synthesis, and the time taken, it is about 2 to 4 minutes. The product will be at this position, the bond will be broken, and the product will be C6H5 COOH. COOH, benzoic acid, and also the yield is about 84%. So, sorry, this reaction, it will be taking at 2.4 minutes. Okay, 2.4 minutes. So here also the yield is about 84% using microwave assisted saponification. Okay. Then the next reaction, that is the oxidation of toluene. Oxidation of toluene. See here, this oxidation of toluene, it is carried out in the presence of alkaline KMnO4. C6H5CH3, oxidation using alkaline KMnO4. Alkaline KMnO4, microwave assisted. It will be taking only 5 minutes, and the product will be, see, any side chain will be oxidized to COOH. So here also the product will be C6H5 COOH, benzoic acid, and the yield is about 40%. The reaction is carried out within a time of 5 minutes. Normally this oxidation will be taking place by reflexing in a condenser, by reflexing using a water condenser, and it will be taking nearly 10 to 12 hours by normal methods of reflexing. Okay. By conventional method, it will be taking 10 to 12 hours, but here it will be taking only 5 minutes to yield 40% of the product. Okay. So these are some of the important reactions or the important microwave assisted organic synthesis using water. Next is the microwave, the second classification, that is the microwave assisted organic reactions using organic solvents. Okay. Second one, write down the heading, microwave assisted reactions. Microwave assisted reactions in organic solvents. In organic solvents. See, the first reaction, we have to go through some of the examples. First is the reaction between carboxylic acid and alcohol. That means it is an esterification reaction, reaction between acid and alcohol. Reaction between acid and alcohol, it is an esterification reaction. It's an esterification reaction. So here, first of all, write the acid, that is C6H5 COOH, that is benzoic acid, COOH plus an alcohol. That is, for example, propanol, that is OH, CH2, CH2, CH3. Okay, this is propanol. CH3, CH2, CH2, OH, propanol, 1 propanol. This is benzoic acid. So here, 1 OH from this benzoic acid and hydrogen from this alcohol will be removed as water, and the remaining will be an ester. So the product will be like this, C6H5 then CO, then O, then CH2, CH3. Okay, so this is an ester. COO group is coming here. So this is an ester. So this particular reaction, it is carried out in the presence of concentrated sulfuric acid and also microwave radiation, then at a time using a time of 6 minutes. Okay, only the time consumed, it is about 6 minutes. And also the yield of this compound, this is phenyl benzoate. Not it is phenyl benzoate, it is propyl benzoate, isn't it? 1, 2, 3. 3 carbon atoms are there. So it is propyl benzoate. Propyl benzoate. So the yield of this propyl benzoate, it is about 70%. Okay. So this is the first reaction using organic solvents. See here, this a small amount of sulfuric acid is added. It is used as a catalyst. And also the yield is about 70%. Then the next reaction, hope you have written. Then the next is the reaction between, second one, that is the reaction between carboxylic acid and benzyl ethers. Carboxylic acid and benzyl ethers, that is the second reaction. So here benzyl ethers are used, that means benzyl N-butyl ether is used. See, benzyl N-butyl ether, the structure, it will be like this. This is benzyl group, C6H5CH2, benzyl group. Then we have to write the ether. So here we are taking benzyl N-butyl ether. Benzyl N-butyl ether. Okay, so benzyl part I had written C6H5CH2. Then you have to write this N-butyl ether. N-butyl means small n means it is normal chain, isn't it? It is a straight chain butyl compound. Okay, butyl ether. That means 4 carbon atoms along with ether group means an oxygen atom will be coming. Okay, so for either 1 oxygen atom, then you have to write 4 carbon atoms also. Okay, so CH2, then CH2, CH3. So this is benzyl N-butyl ether. Okay, this is benzyl. Okay, I am not writing it again. So this is benzyl N-butyl ether. Hope you understood how to write the compound. And also this benzyl N-butyl ether, it reacts with an acid. Reaction between an carboxylic acid that we are writing here. So this will be reacting with acetic acid, CH3COOH. So here what happens is that this CH3CO group, it will be joining at this ether portion. Okay, at this portion, that is, it will be combined, that is, the bond will be broken here, and this C6H5CH2OCOCH3. That therefore we will be getting an ester, isn't it? So here the solvent used is lanthanum bromide, that is LNBr3, lanthanum bromide, LNBr3. Here lanthanide elements we are using, sometimes we are using lanthanum, or sometimes neodymium or samarium can be used instead. Okay, so it is tribromides, lanthanum tribromides are used as a solvent here, and the reaction, it is carried out in microwave conditions and will be completed within 2 minutes, and the product formed will be C6H5 CH2O, then COCH3, OCOCH3. So it is an ester combo, ester, isn't it? OCOCH3, and the remaining you have to write, that is CH3, CH2, CH2, CH2OH. Okay, CH3, CH2, CH2, CH2OH. So how many carbon atoms are there? 4 carbon atoms are there. So it is butyl alcohol. OH group, it is alcohol. So this is butyl alcohol. The byproduct is butyl alcohol. And the major compound, this is an ester. So this is benzyl acetate. So this particular part, C6H5CH2 is benzyl, isn't it? Benzyl, and the remaining will be, this part will be acetate. Okay, benzyl acetate. So here also the solvent used is lanthanum bromide, lanthanum tribromide. Reaction will be completed in 2 minutes. Normally this particular esterification reaction will be taking 10 hours to complete. See the difference? Say just within 2 minutes the reaction is completed. By conventional method it will be taking 10 hours to complete that particular reaction. Okay. Then the next reaction, that is the Fries rearrangement reaction. Hope you had written this reaction. Then the third one, Fries rearrangement. Fries rearrangement. Fries rearrangement. See this Fries rearrangement, it is used for the preparation of this phenolic ketones. Phenolic ketones, that means the formed compound, it will be having keto group as well as OH group. Okay, so that is the Fries rearrangement reaction. And here this one of the substrate used, it is paracrysyl acetate. Paracrysyl acetate. See, I am writing the structure as well. C6H5 O CO CH3. Then at this position, para position, there is a methyl group. Okay, so this compound, it is paracrysyl acetate. Paracrysyl acetate, or otherwise another name, that is 4-methyl acetophenone. 4-methyl acetophenone. 4-methyl acetophenone. See, fourth, this is 1, 2, 3, 4. At the fourth position, a methyl group is there. Then this is the aceto group, CH3CO aceto group, then phenone. Okay, C6H5CO group. Okay, so this is 4-methyl acetophenone. So this compound, on treating with aluminium chloride, AlCl3, aluminium chloride, in the presence of aluminium chloride and chlorobenzene. Aluminium chloride and chlorobenzene, then microwave radiation, 2 minutes. The reaction will be completed within 2 minutes. And the product, it will be like this. I will be explaining the reaction. Write down the product first. See, the product will be here. At the first position, there will be OH. Second position, there will be COCH3 group. And at the fourth position, there is a methyl group. Okay. So here, what happens is that this is a rearrangement reaction. Okay. See, at the second position, there is a hydrogen there. So what happens is that rearrangement will be taking place, and this hydrogen will be going to the oxygen atom, and this COCH3 group, it will be coming to the position of hydrogen atom. Okay, so this hydrogen will be joining here at the oxygen atom, so it becomes OH. Okay, it's OH. Then again, in the second step, this COCH3 will be moving to the second position, and it will be COCH3. And already at the fourth position, there is a methyl group. Okay, so this is the product formed. So this reaction will be carried out in a microwave oven for about 2 minutes. And also the yield of this particular reaction, it is about 85% we will be obtaining. Okay, so this is another reaction, that is the Fries rearrangement. Then the next reaction, that is the oxidation reaction. Oxidation reaction. So here, oxidation of toluene. Oxidation of toluene, that is C6H5CH3 in the presence of potassium permanganate. The solvent used is potassium permanganate. And see, again, the side chain oxidation will be taking place, and the product formed is benzoic acid, C6H5COOH, benzoic acid. The yield is about 40%. This is toluene. The yield is about 40%. This reaction, it is microwave assisted. The time taken will be 5 minutes. Okay, so this is another reaction, oxidation reaction in the presence of a solvent. So these are the some of the reactions which are carried out in presence of solvents. So that is regarding about the second category, microwave assisted reactions using solvents. Then you have to go through this microwave assisted reactions in the solid state, the third type of reaction. Microwave assisted reactions in solid state. Microwave assisted reactions in solid state. The first reaction, that is deacetylation. Deacetylation. See, deacetylation means the term De means it is the removal of a particular group. Removal of any group we can call it as D. That is, dehydration means removal of water. Dehydrogenation means it will be removal of hydrogen. See here it is deacetylation. So it will be removal of this acetyl groups. Okay. So here this normally some of the aldehydes or phenols, they are protected by this acetylation. That means OH group or COOH group or CHO group, they are protected by this acetyl group, that is CH3CO group. That means to this OH group is protected by this using the CH3CO group. So in such cases, once it is converted to acetyl compound, after completing the reaction, we have to get back that OH group. So for that we are using this deacetylation reaction. Okay, and usually this will be done, this deacetylation process will be carried out under acidic or basic conditions, and also usually it will be taking a very long time for completing this deacetylation process, and also the yield will also be very low. But while using this microwave assisted synthesis, the yield will be very high, and at the same time the time taken will also be very low. For example, benzaldehyde diacetate. Benzaldehyde means C6H5CHO, isn't it? So this oxygen atom, it is replaced by 2 acetyl groups. Okay, that means 2 OCH3. So I am writing it as C6H5CHOAC. That means OAC means acetyl groups, or we can write it as CH3CO twice. Okay, so C6H5CHOAC twice. This, instead of this oxygen atom, this aldehyde group is protected by this acetyl group. Okay, so here this reaction, it is carried out in presence of natural alumina. In presence of natural alumina, microwave assisted, taking the time taken will be 40 seconds. The product will be benzaldehyde C6H5CHO. Okay, the product is benzaldehyde. So this is one reaction, microwave assisted reaction in solid state. Then the second reaction, that is the debenzylation of carboxylic esters. Second reaction, debenzylation of carboxylic esters. Debenzylation of carboxylic esters. Normally the carboxylic acid groups are protected by using this benzyl group. Okay, so here debenzylation means it is the removal of the benzyl group. So the reaction, it will be like this: C6H5, then COO, CH2, C6H5, COO, CH2, C6H5 in the presence of acidic alumina, microwave assisted, time taken will be 7 minutes. The product will be, see here at this point what happens, the bond will be breaking, and the product will be benzoic acid, C6H5COOH, and the yield will be 92%. So this is another reaction using this microwave assisted synthesis. See, the time taken, the time will be completed within 7 minutes itself. Normally it will be taking a very long time for the reaction. And also if it is taken in an oil bath, instead of water bath, we are taking an oil bath for completing the reaction normally. At that time also it will be taking about 20 minutes to complete this particular reaction. But instead, see here, it will be completed within 7 minutes or within 10 minutes of the particular reaction. Then the next one, the third reaction, that is the oxidation of arenes to ketones. Oxidation of arenes to ketones. Oxidation of arenes to ketones. See, normally arenes are oxidized to ketones. That means arenes means a double bonded compound. It will be converted to CO group using this microwave assisted reaction, and the time reaction will be completed within 30 minutes of the start of the reaction. Okay, so consider this particular compound C6H5, then a 5-membered ring in between, two benzene rings. Okay, so this is an arene, and also in the presence of KMNO4, the reaction, since it is an oxidation reaction, it will be carried out in the presence of KMNO4 on alumina. potassium permanganate on alumina. The time taken will be 10 to 30 minutes. Microwave assisted synthesis. The product will be, see at this position, the CH2 group here, it is having a carbon atom and 2 hydrogen atoms, isn't it? So the CH2 group is converted to CO group after the reaction. Okay. So the product will be like this. Double bond O, then again a benzene ring. Okay. So this is the reaction. So oxidation of this particular arenes to ketones. Then the next reaction, reduction reaction. Reduction using sodium borohydride, NaBH4. Reduction using sodium borohydride. Normally, carbonyl compounds will be oxidized to alcohols by using this reduction. That is, CO group will be reduced to CH2OH. Aldehydes or ketones will be reduced to alcohols. So here we are using sodium borohydride in the presence of alumina. Okay. So you have to write this particular reaction R C6H5, then C double bond O, then R dash. Okay. This is the keto group. So here we are using NaBH4, sodium borohydride, as the reducing agent in presence of alumina. In presence of alumina, and microwave radiation is passed through it, or it will be conducted in a microwave oven, and the time taken will be between 0.5 to 2 minutes. Within that fraction of that second itself, the reaction will be completed, and the product will be, see the CO group, it is converted to COH. So R C6H5, then C, here it will be OH, then R dash H. Okay, CHOH R dash. The yield will be about 62 to 93%, the product yield. Okay, and also this particular reaction, see, in the presence of reducing agent sodium borohydride in alumina, microwave assisted, time taken will be 0.5 to 2 minutes. The yield will be 62 to 93%. The CO group is converted to CHOH. Okay. Then the next is the last reaction, that is the reduction of carbonyl compounds. Reduction of carbonyl compounds, that is CO group, with aluminium alkoxide. With aluminium alkoxide. With aluminium alkoxide. See here, a keto group R, C double bond O, R dash, a ketone, plus isopropyl alcohol, that is CH3, CHOH, CH3. Isopropyl alcohol. The reaction will be carried out in the presence of aluminium alkoxide. The reaction will be carried out in the presence of aluminium alkoxide, microwave assisted reaction. So the product will be, first the CO group will be converted to CHOH. Okay, so the product will be R CHOH R dash plus CH3 CO CH3. Okay, CH3 CO CH3. So this is another reduction reaction. So these are the three categories of reaction, that is, so here you have to go through these three things. That is, the first one, that is a microwave assisted synthesis. What are the advantages of using this microwave assisted organic synthesis? Then the three types of reactions, that is the first one, microwave assisted reactions in water, in organic solvents, and in solid state. Okay, so all of you should write the lecture notes as well and submit in our Google Classroom as usual. Okay, so then the next topic, that is the ultrasound assisted organic synthesis, that we can see in our next session. Okay, thank you.